Question number 4. A scientist investigated a sample of radioactive material to determine if it would be suitable for medical use. 4.1 is an AO1 question, and this question is from the topic of radioactive contamination. The method, results, and conclusions of the scientist will need to be checked by the other scientists before the result of the investigation are published. What name is given to this checking process? Before publishing, the results, conclusions, and method are reviewed by the other scientists. This process is called peer reviewing or peer review. So the correct answer is peer review. Four point two is an AO1 question, and this question is from the topic of radioactive decay and nuclear radiation. There is an increased risk of cancer if the scientist is irradiated by the nuclear radiation. What property of nuclear radiation causes the increased risk of cancer? The property which is involved in cancer is that is ionization of the body cells, because the nuclear radiations have the property that they can ionize the body cells, which can lead towards cancer in the body. Therefore, ionizing property of the nuclear radiation is responsible for increase of the risk of cancer in the scientist. Let's see the model answer. Ionizing property of the nuclear radiation is responsible for causing the risk of cancer in the body of the scientist. 4.3 is an AO1 question, and this question is again from the radioactive decay and nuclear radiation. The activity of a radioactive source is the rate at which the nuclei of the source decay. What is the unit of the activity of a radioactive source? The unit of the activity of the radioactive source is becquerel or BQ. The unit is becquerel or BQ after the name of the scientist Henry Becquerel. 4.4 is an AO1 question, and this question is again from the topic of radioactive decay and nuclear radiation. The scientist placed a radiation detector near the sample and measured the count rate. Explain why the count rate is less than the activity of the sample. The reason behind it is because the radiations are spreading out in all directions. A few of the radiations are entering in the detector. Therefore, the count rate is less than the activity of the sample. Let's see the model answer. As radiations are spreading out in all directions, therefore, all emitted radiations are not entering in the radiation detector. As a result, some of the emitted radiations are detected by the radiation detector or reaching the detector. The mark distribution is already given here. 4.5 is an AO1 question, and it is from the radioactive decay and nuclear radiation. The scientist recorded the count rate from the sample with the radiation detector at different distances from the sample. Table number 2 is shown, in which the distance is given in centimeter and the count rate is given in counts per second. Explain which type of radiation was emitted by the sample. If you look here, as the distance is increasing, the value on the count rate is decreasing. So we will assume that the radiation which is emitted by the source is alpha radiation. We can see from here, as the distance is increasing in centimeters, the value on the count rate is decreasing, because alpha particles travel at just a few centimeters in the air. Let's see the model answer. The radiation which is emitted, that is alpha radiation, because alpha radiation travels a few centimeters in the air, and from the above data the radiation is not detected beyond 5 centimeters. We see here after 5 centimeters the value is 0. Beta radiation can travel a few meters in the air, and gamma radiation can travel hundreds of meters, even kilometers in the air. The mass distribution is given along the answer. 4.6 is an AO3 question. The student need to use the knowledge and apply the knowledge and analyze the data given in table number 3. This question is from the topic of half-lives and radioactive decay. The scientist moved the detector closer to the sample and started a stopwatch. The scientist measured the count rate from the sample at different times. The table number 3 is given here, the time in minutes, and the count rates as counts per second is given in the second column. The scientists realized that 30 minutes is a whole number of half-lives, that here the count rate is coming in a whole number. Calculate the value of x in the table. Students, they make the mistake. They understand that 30 is the first half-life. If we take 30 as the first half-life, it means the number of nuclei will get half. It becomes 784. This is the first half-life. If we have the second half-life, which is again 30 minutes, it becomes 60. The answer should be 392. But in our table number 3, the answer is 98. The students usually make a mistake. They consider 30 minutes as the first half-life. Let's see the model answer, which can help us to understand what is the value of x at the time of 30 minutes. In our model answer, the time is given in minutes and the count rate is given as counts per second. We will keep dividing our count rate until we will get the value 98. We will use the concept of the half-life. For the first half-life, we will divide it by 2 and the answer is 784. If we divide by 2, that is our second half-life, we will get the answer 392. After the third half-life, we will divide the value 392 by 2, the answer is 196. And we need to divide 196 by 2, we will get the answer 98. We used 4 half-lives and the total time for these 4 half-lives is 60 minutes, which is given in table number 3. So we will divide 60 by 4, the answer is 15 minutes. So time of the first half-life is 15 minutes. The second half-life, that is 30. Third half-life is at 45 minutes. And the fourth half-life is at 60 minutes. And the answer is 98. So the value of x in our question is 392 count per second. Therefore, the 30 minutes is the second half-life, not the first half-life. And the count rate is 392 counts per second. 4.7 is an AO3 question, and this question is again from the topic of half-lives and radioactive decay. The scientist had a second sample of radioactive material. The scientist made appropriate measurements, then calculated the half-life of each sample. Why was the half-life calculated from the second sample slightly different from the half-life calculated from the first sample? Pick one box and we have 4 different options given here. Radioactive decay is a random process. Second option is the count rate from the radioactive sample is predictable. The third option is the samples were at different temperature. The fourth option is the size of each sample was different. The count rate is not affected by the temperature. The size of the sample is not affecting the half-lives of the sample or the radioactive substance. The count rate from the radioactive sample is predictable. It is not a predictable process. Therefore, we can say that the radioactive decay is a random process. It is not a predictable process. So the correct answer is a random process.